Hey, Gene. Oh, you get power there?
Yeah, I do.
Oh,
With my converter.
you didn't need a converter?
What?
I didn't need a converter in my room.
Well, just something that will plug into the
Over
time.
there. Yeah, I plugged in on mine over
Oh,
there.
you have the
It didn't
ability.
work. Yeah. Okay.
You would have a thumbtack for a paper clip. You can get a thumbtack outside near the post. There's a cup near the poster.
I like about you. You're so resourceful.
Huh?
That's what I love about you. You're so resourceful.
What?
Resourceful.
Oh, I am a resourceful.
You always know where things are.
ああ、そうそうそう。意外となんか帽子を落としたら、それを拾ってから、大使館の中の人が、逃げてる人が、わからない。英語で書いてある。
ちょうど前の日だ。
Mine, yes, mine. I've had it for quite a while. Video. I mean, same one I had for
Well, I think the speaker is live, so I've got the tape recorder hanging Well,
It's not loud enough. Are we ready? We are going to start. So, if anyone still in the lobby or in the corridor, please come in. We are very glad to have all of you here, and the leadership of Tsinghua University will give us a welcome speech. Professor Zeng Kang, Vice President of Tsinghua University, will speak first.
抱歉啊，这个我用中文跟大家都表示欢迎。
I'm sorry, I speak in Chinese.
女士们、先生们，
Ladies and gentlemen,
欢迎你们来参加 ICCF。
welcome to ICCF-9.
由于你们来到了北京，来到了中国清华园。
Welcome to Beijing, welcome to China.
由于你们的到来，使清华大学生意盎然。
Tsinghua University garden is blossoming for our guests from all over the world.
我听陈教授说，你们呢都是很有成就的，你们的研究工作，正在取得新的成果。
Professor Chen Nengquan said, this research field is blossoming as well.
有100多篇的论文摘要寄到本次会议。
More than 100 abstracts have been submitted with very interesting results.
并带来了许多令人振奋的消息。
It's very exciting.
在今年的3月8号，科学家志迈出了重大的一步，来实现他的使命。
on March 8th, Science magazine made a great step towards its mission, that is, to put interesting, potentially important science into public.
这把最有兴趣的、有潜在意义的重大科学告诉了大众。气泡聚变的研究成为人所共知。
Bubble fusion become popular in the world.
气泡聚变的作者也正表示，愿意出席 ICCF-9， 并做大会报告。
The first author of that bubble fusion paper replied to us very kindly that he would have liked to provide a talk in ICCF-9.
由于时间过于紧迫，未能如愿，他致函祝贺，为本会成功，祝愿本会成功，并提议我们访美时共同讨论感兴趣的工作。
Due to the time limit, Dr. Telayakan is not able to come. Instead, he sent us his best wishes for a very successful ICCF-9, and he proposed a discussion for our mutual work in the future.
清华大学一贯支持基础研究，鼓励创新，发展交叉学科，对你们的工作表示充分的理解和支持。
Tsinghua University support the fundamental research constantly. We encourage the original work and develop the interdisciplinary science. We fully understand your work and support your work.
在我们学校新落成的清华紫光国际教育中心举办 ICCF-9， 就是有力的证据。
It's a strong evidence that the ICCF-9 will be held at brand new Tsinghua University Center.
我谨代表清华大学欢迎各位女士、先生们远道到来。
On behalf of the leadership of Tsinghua University, welcome all the distinguished guests.
欢迎马丁·弗莱希曼教授，欢迎方田基明教授和杜兰教授，以及格里亚列切夫教授。
Welcome Professor Martin Fleischmann. Welcome Professor Arata. Would you please stand up, Professor Arata? Where are you? He's preparing his talk after Martin. Welcome, Professor Tom Dolan. Please stand up. Welcome, Professor Golyachev from Kolchatov Institute. Ready?
Too early.
Okay. Go ahead.
我由于时间关系，我不能一一的列举各位贵宾的名字，但我要衷心的祝贺我们各位贵宾，在北京期间能够身体健康，心里愉快，并祝愿我们这次大会能够成功圆满。谢谢大家，Thank you。
of the time limit, I cannot name every distinguished guest. However, I would like to express my sincere wishes for a great conference and for your health, and hope you have time to visit our beautiful campus. Martin, would you like to say something?
Well,
Let me push the button. Yeah, or the micro.
okay. I think we are all extremely pleased to be here. I think what we see. You can't hear. All right, now sit down and speak. We are all extremely pleased to be here. And I think this meeting shows that this topic is not like most other new topics, because usually what happens is there is a new field of research, it dies. And then it starts again and it dies a second time. Now, if it starts a third time and continues, it will succeed. If it dies the third time, it's dead. But this topic has not died. We have experienced a lot of trouble in keeping it alive, but it has not died. So this may be the first time that a topic continues until it is successful. And I think there are indications that maybe ICCF-9 will be very, very large. That in fact that there are many pathways to low temperature nuclear reactions, which is of course a very tricky concept to put forward, but I think this will become established. So, Mr. President, we are very pleased to be here. We look forward to taking part in this debate. And I would just add that in China, you are developing into the 21st century. This is a topic, I think, ideally suited to a society moving into the 21st century. So we wish you well, and we are extremely impressed by all your efforts here.
Thank you. Now, I would like to just introduce some of our important people here. Professor Tsinghua, the backbone of this research in China. Okay. And Professor Xing Zhong Li, the honorary co-chairman of ICCF-9. I cannot name everyone, but right now I try to express my sincere gratefulness to the contributor. The first is Professor Chen just reminded me to mention Professor Yang Liming of Beijing University. He is the honorary co-chairman of the program committee. Unfortunately, he got a serious disease in his brain, have to be in the hospital for surgery. So we hope he will come back, become our another backbone also soon. We have another chairman for our program committee. That's Professor Fu Yi Bei. Because his schedule is very, very crowded. He tried to be here, but he couldn't. Among them, I try to mention one of the hot fusion scientists here. That's Professor Wang Yuanxi. He was the, oh, just stand there, the back seat. You can come here. He is one of the top leaders for the hot fusion in China. It's unusual with such an open mind. But he is not alone. Professor Tom Dolan from Idaho. But you look at his tie, same as mine. That's from IAEA, the International Atomic Energy Agency, Vienna. Last year he was the leader there for the fusion research for United Nations. This is evidence. The book, 3 volumes book for the fusion research. It's available through the CD from the IAEA. Such a famous scientist believe we should work on the low energy nuclear fusion. Of course, he is not alone. We have to mention I cannot mention everyone, but I have to mention some of the contributors for this conference. Professor Zhang Zhaoqi, is she here? Zhang Zhaoqi, the ex-editor-in-chief of Tsinghua University Press. Mr. Wang Mingliang, is he here? He is the head of Tsinghua Tongfang Optical Disc Corporation Limited. Professor Wang Dianru, he is the general manager of the Great Wall Titanium Gold Corporation Limited. Dr. Chen Yuqian, please stand up. He is a representative from Nanometer International Company. They all contribute to this conference to make it possible. Thank all of you. Okay, right now just we follow the schedule, 9 o'clock. We have to start our morning session. Before we start, let's say thanks to our leader, Tsinghua University leader. He is very, very busy. He come here just for welcome everyone. Now you first, then we start the session. Thank you. I just say a few words, then we go. So everyone noticed that the schedule changes once and once again. This is supposed to be the final. And everyone has an abstract book, the back side, the cover page on the back. This one is the original one, but we changed it. So everyone get another separate sheet with two sides. This one and this one. Do you have this one? Yes. Okay, yeah, good. This is supposed to be the final. And according to this final schedule, after the opening session, Martin will give us a very exciting speech. After his speech, Dr. Dimino and Professor Judich will give the introduction each other. Then after coffee break, we started the second session, and Dr. Tom Purcell and Professor Arata will give the speech. And everyone look at the back side of the desk. Professor Arata is so enthusiastic to give his knowledge to us. He sent us by the express mail for these 360 preprints. Make his speech understandable. So if you have not this in your hand, you can take these copies during the coffee break. Right now, I just want to mention, after the morning session, we will take the conference photo. After the conference photo, we will have the lunch. And this evening, we will have a very unusual industrial discussion. Professor Moods, please stand up. Professor Moods from Great British for his famous sputtering process in order to avoid the flake off problem. So this is only one evening session in our conference. This evening, 7 o'clock here. All of you are welcome to join this industrial discussion on the flake multi-layer thin film flake off problem. Someone told me he solved or she solved this problem. Someone told me this is a big problem. Now let's join us for this exciting industrial discussion. Now let's start the morning session, the first talk. We move and then you put something here, equipment. We start. Okay. Thank you. Be careful when you get down. Be careful. 重新这里有点。狗听真是下一句。
Thank you. You saved them.
I'm not ready. This is new for me. This is a timer. The timer, you are supposed to have 1 hour speech, right? So I will make the timer round on that.
Shall I start now?
Have you got a microphone?
Well, ladies and gentlemen,
Oh, the microphone. Microphone. Maybe we should turn off some of the 关掉一些灯吧，这前头灯请你稍微关一下。
ladies and gentlemen, can you hear me now? No? I'm not in favor of modern technology. I shout. Is this better? No. Just the mic. Let's see. Is this dead?
I think.
How about this one?
Ah.
The other one now. Let me just say that I think before we start, we should thank Professor Li for organizing this conference. And personally, I'd like to express my appreciation to Professor Li and to Professor Tian, who's here with us here today, for the invitation to give this talk. Now, I had some difficulty with this talk, scientific difficulty, because I have talked extensively on previous occasions about this topic. So, in a sense, there is not that much new which I can add. However, I think I can explain some of the background to it, and let me just start by I don't know.
Maybe put another piece of paper on it.
That's okay. I think the view has been expressed that we decided suddenly to go into the laboratory, charge some palladium electrodes, and see what happens. Now, of course, this is true. We didn't one day decide to go into the laboratory and start this research project, but it had taken quite a long time to get to that position. Actually, it took me 36 years to reach the decision to start this project. And it took Stan Pons, my ex-colleague, rather shorter time. He had done some work in Canada, which convinced him that this might be possible. They didn't follow that it would be possible, but it might be possible. And because we were working together in Salt Lake City, we reached a critical mass of 2, which is required to start a crazy idea like this. Now, the reason I thought I would cover some of the background is because we are, in fact, in a very strange situation, which is relevant to some of the I think we are in difficulty. Okay. There. We are in the strange situation that it is becoming possible to, the work has advanced to the point where we might ask, what else should we do? And it is that which I think has persuaded me that I should spend a little time this morning on giving you the background to this work, which caused me to start this particular venture. So really what I want to try and do is to explain what happened prior to 1983 which caused us to start this venture. Now, all this work was part of a general program aimed at trying to find illustrations of the need to invoke the quantum electrodynamic paradigm. Now, you are all familiar with the classical theoretical physics and with quantum physics, and many people believe that this is sufficient. Very good. Except we have to move it. Okay. That this is a sufficient basis for understanding the natural world. But in fact, I became quite convinced early on that it was not a sufficient basis. And I asked the question, is it possible to develop electrochemical experiments which demonstrate the need for this paradigm? And our initial work was concerned with these topics here: the effects of time and space, length, dimensionality, number, and structure. So this prior to 1983, I'd done a great deal of work which was in this field, only I had never revealed the fact that I was really looking for illustrations of quantum electrodynamics. So let me go back at this point in time to about the late 1950s and early 1960s and show you what convinced me that we needed to think about processes in solutions in terms of quantum electrodynamics. Now, this is an illustration of the measurements of the kinetics of very fast reactions. We were interested at the time in the kinetics of very fast reactions of ions in solution. You have an undissociated acid HA, a dissociated species H plus and A minus, and the question is, how can we measure these very fast kinetics of reaction? And as you may know, Professor Eigen got the Nobel Prize for his work on the relaxation technique. And this could all be interpreted, I'm having a hard time here, it could all be interpreted in terms of randomization of the structure by the usual mysterious thermodynamic processes at long length scales, and the recombination of ions by the diffusion control process, which is the model of Debye. And the view which gained ground was that all the processes could be interpreted in terms of this randomization and the diffusion controlled reaction. The question, of course, was this correct? And we, at that time, my colleague in the University of Newcastle, built this was mainly done by temperature jump methodology. You take the system and you perturb the temperature, and the perturbation in the temperature causes a change in the concentrations of the undissociated and dissociated species, and if these are colored, you can follow the transient on a microsecond scale. We built another instrument which had a much higher time resolution. The time resolution of Ivan's instrumentation and other people's instrumentation as well was about 10 to the minus 5 of a second. That fixes the length scale, which we are looking at about 10 to the minus 5 of a centimeter. I'm very old-fashioned, so I have to use the old CGS units, which makes the space-time about 10 to the minus 10 centimeter seconds. Well, we built an instrument which had a higher resolution and actually investigated coupled reactions in solution. I think I should stand on the other side. No.
Take away this desk.
No.
This will block. We take away this desk.
Yes.
Okay.
It would be better without the desk.
Yeah.
I'm preparing the way for other people.
Yeah, I deduct the time.
I don't think you can do this.
啊，把这个桌子可以拿掉，因为这儿挡掉一大块。
I think this is going to cause terrible confusion.
Yes, yes. Help us move the desk. You are stronger than I am.
Are there any more volunteers here? Eureka, as Archimedes said. Next time I'll bring it on a laptop. You cannot have an old-fashioned presentation in this day and age. Well, the important point about this, the methodology we adopted, was that the time resolution was faster. I should explain to you that we were very fortunate that the Harvard Zeta program, which was the first hot fusion program, had collapsed in confusion, but the pieces of equipment were still available. So this apparatus was built out of what was left over from the Harvard Zeta program. And the time resolution was about an order of magnitude greater than that of Eidel's experiment. And we were looking at coupled reactions in solution. Now, of course, when you have two coupled reactions in solution, you should see two relaxations, which we did in fact see. But when we tried to deconvolute the rate processes into the individual rates, we found that the rate constants were phase related. Now, you cannot conceive of such a situation unless there is a memory propagator in the system. And that memory propagator, since we had moved from a length scale of about 10 to the minus 5 centimeter to 10 to the minus 6 centimeter, there had to be some factor in the solution which was associated with the memory propagator, which was of the order of 100 angstroms in dimension. I think I should pause while this other modification of my old-fashioned technology is taking place. I did once give a lecture in France, in Perrin's lecture theatre, and I had to adjust to an epidarscope, which was very difficult, I think. That's all right. Leave it, leave it. Leave it, leave it. Well, of course, it may be that we can interpret all reactions in solution in terms of randomization by some mysterious thermodynamic process and diffusion-controlled rates. But the fact that we have this change in the kinetics implied that we had a memory propagator. Now, this was not the only. In fact, I found, as a chemist, I found it very difficult to believe that if we saw a diffusion-controlled rate of recombination of ions, that this meant that all processes were limited by the rate of diffusion, the encounter rate. As a chemist, I would say, well, this can obviously not be so. And there was some prior experience in electrochemistry where you can measure the rates of reactions in solution by perturbing the equilibrium at the surface of an electrode. This is an electrode, there's no species HA present. We only have, Professor Li, I have to look at whether I can have lost my watch now.
No way.
What are you looking for?
My watch. Fantastic. I will put it here. There had been some earlier experiments, and these experiments showed that the rates in these systems could be in excess of the encounter controlled rate, the Debye limit. Now, because the physicists talked very loudly about this project, and the electrochemists had an inferiority complex, they decided that the electrochemical experiments had to be wrong. And this was, in fact, the situation. They believed it was wrong. But we also did some work which has a bearing on our present topic. We made some special purpose experiments where we perturbed the concentration of protons at an interface of a palladium hydrogen electrode, and because of this phase discontinuity, we could have a greatly, about 6 orders of magnitude increased rate of recombination, and we could measure the recombination of the ions at the surface of the electrode with protons generated at the palladium hydrogen electrode. And there we found, to our not very great astonishment, that the rate of recombination could be, instead of the Debye limit, which is about 10 to the 11 liter per mole per second in chemical units, 10 to the 14 liter per mole per second, which is the rate you would calculate if the rate of recombination is determined by the hydrogen bond frequency. Clearly the dynamics of the processes are vastly different to the ones we would set up. And at that time, I also was much concerned with thinking about the general modeling of processes in solution. And as you know, this is the familiar model of the Debye-Hittel theory of a central ion surrounded by a space charge. And this is a purely electrostatic model. Now, of course, we are not dealing with electrostatics. We are dealing with dynamics. The particles are moving, if we accept the Einstein model, the particles are moving by Brownian motion. At the points the particles are at rest, and in between whilst they accelerate and decelerate, and consequently, of course, the system has to radiate energy. Now, if we think what we are doing in the modeling of the system, we are modeling the system as though it were static, but it is dynamic. If it is dynamic, the model actually violates the second law of thermodynamics. It's not microscopically reversible. So it won't do. And somehow this is associated with the structure of the order of 10 to the minus 6 of a centimeter, 100 angstrom structure. Now this remained an absolute mystery to me. I did not know how to proceed with this. I knew the explanation lay in quantum electrodynamics, but I did not know how to handle this topic until I got into touch with Emilio Del Giudice, who's here, and the late Professor Preparata. And they developed a model of water, which postulates the essential, the application of quantum electrodynamics to water shows that the water must be divided into 2 domains, a coherent domain and an incoherent domain, and the ions are confined to the incoherent region where they execute coherent dynamic motions. And in fact, we have applied this to the behavior of electrolyte solution, a paper which has excited monumental little interest. But we have gone on to look for applications of this model. I think my Italian colleagues don't want to talk about this, but I will try not to resist saying that if you have a model, you should ask what else can it tell you. And here I would like to show you the extremely interesting experiments by Professor Jardin in Russia, which shows that the imposition of a static magnetic field and an oscillating magnetic field leads to an increase in a resonant phenomenon in the electrolytic conductivity. This is for glutamic acid, but we've done it for other systems as well now. And I thought I'd show you this because it shows you that the interpretation, the application of quantum electrodynamics to a physical system always produces somewhat unusual results. And the unusual result in this particular case is that, of course, the application of the weak alternating magnetic field okay, let's see whether we do better. The application of this weak alternating magnetic field leads to the extraction of ions from the boundary region of the coherence domains, so that you get an increase in the ionic concentration, and it leads to a resonant increase in the electrolytic conductivity. So what in fact is happening is that the application of the alternating, very weak alternating magnetic field, very weak compared to the Earth's magnetic field. The static field is comparable to the Earth's field. The alternating field is weak compared to the Earth's field, leads to the generation of a battery. Now that should not surprise an electrochemist, but it is somewhat surprising that a weak magnetic field leads to the development of a battery in the system. Of course, it has been known for a long time by biologists that weak alternating fields have a marked effect on biological systems. And at VHS, I said that because the physicists could not understand it, they always produced papers which implied that the experiments had to be wrong. But that is a very understandable position in science. But I think we should also say to ourselves, what if the experiments are right? What can be the possible explanation? Gosh, I have to be faster. Well,
Take your time, don't worry.
we resolved, I must tell you that the ideas I had at the time had a very bad reception. There were two classes of people. There was one theoretical physicist to whom I presented these results. He said, it's quite obvious you have to work in terms of quantum electrodynamics. His interest was chromodynamics, quantum chromodynamics. And I said, yes, but I don't know how to do it. Everybody else said, you are mad. I mean, this is a situation I've frequently been in, that people say you are mad. And so I decided that we had to, if we wanted to explore the application of quantum electrodynamics, whether this paradigm was valid in physical systems, we had to do it in secret. We had to follow a secret agenda. We had to decide, work on the system as it was described on the left-hand side, and then have to ask ourselves whether the description requires the application of quantum electrodynamics. Now, I think that is really a sensible strategy, because it may not be that the system requires an interpretation in terms of quantum electrodynamics. We can simply stop, so we don't bias our investigation. So, I haven't time to give you all the details of what the research we did. I'll just give you one other example. We thought we had to work on small structures, and here is one which may be familiar to you, a small structure. You know our body, our biological systems contain membranes, and many of the processes are controlled by transduction of ions through a membrane. So this is a representation of a lipid bilayer, a black hole, a black lipid bilayer, and a narrow hole induced in this by a pore-forming molecule. And we can ask ourselves right at the beginning, is this a possible structure? Well, you can see we have three phases. We have two components, and if we apply the phase rule, we see that the number of phases, 3, plus the number of degrees of freedom, 2, is not equal to the number of components, which is 2 plus 2. So this system, the biological system, violates the second law. This is an application of the second law of thermodynamics. It violates the second law of thermodynamics. So all through this research, I have been concerned, I have thought that we can look for illustrations of the need to invoke quantum electrodynamics in terms of, by starting off by asking whether there are violations of the second law of thermodynamics if we don't follow the quantum electrodynamic pathway. Now, Emilio Del Giudice Abani, you and Caparata have a paper which says, in fact, that the existence of this object demands quantum electrodynamics. So I won't rehearse this argument. I'll keep this for a later presentation. Well, it's been known for a long time that if we have a pore-forming molecule like alanethicin, which is a polypeptide, we get discrete conductance states in the membrane. And that's why. And this is an actual section of a time record of the transmembrane ion conductance, showing transitions between adjacent states. Note there are only transitions between adjacent states. And we showed quite a long time ago now that, in fact, I should point out that this is an ideal object for investigation by electrochemistry because we can get the energetics in each state by the residence time from the Boltzmann law, and we can count the number of transitions, so we can do the kinetics at the molecular level. And we showed a long time ago that it was strictly a birth and death process. We only had transitions between adjacent states. We could also get the energetics of this object. And what turned out, unsurprisingly, I must say, that there was an upper reflecting state, that the electrochemical free energy had a parabolic form, so as the pore tried to expand, it was again constrained to return to zero size. Now, if you know anything about phase growth of materials, you know that the two-dimensional phase growth, the expectation is that the bulk energy should be negative and the edge energy should be positive. So we have an upper absorbing state, and when you have nucleate a two-dimensional structure, it should eventually expand. However, fortunately for us, this is not the case in the biological system. There's an upper reflecting state, so the bulk energy must be negative, must be positive, and the edge energy must be negative. And this is, in fact, if it was not that way, life would not exist. And the question is, why can we have this situation? And the only reason we can have this situation is because the pore is filled by the incoherent domain of the electrolyte, which has a positive energy with respect to the coherent domain. So, because the pore is filled by the incoherent domain of the electrolyte, it has a positive energy. And we get an upper reflecting state. Now, there's another very interesting point here, and that is that, as I've already said, the system follows strictly a birth and death process. However, the pore, if you work out what is actually happening, you see that the pore is empty for much of the time. There are no ions in the pore. Well, if there are no ions in the pore, it can't conduct. If there are no ions in the pore, therefore the current time record should also returns to zero, and it should not be a birth and death process. It should show also transitions between all states. Now it doesn't do that, so obviously there is something wrong. What is wrong? The thing which is wrong is that we are in the wrong paradigm. And I should point out that, let me just point out what the real model is. The real model is that the system is in a single quantum state. A topic which is familiar from the field of lasers. And because it is in a single quantum state, it doesn't make noise. So you do not see the transitions between the ground state and the higher states. It is free of noise. So I also say that in seeking the illustrations of quantum electrodynamics, we have to look for a consistency in the interpretations. Now, if we try to interpret this object in terms of classical mechanics, we get inconsistent interpretations. We get inconsistent interpretations in setting it up. We got inconsistent interpretations in understanding the behavior. Now, the usual pattern in the approach to quantum electrodynamics is to say we have to have a mathematically complete interpretation. So I would say, indeed, we have to have these 3 points, and we have to have a mathematically complete theory. However, I think if you see some of the debate which surrounded cold fusion, we can argue forever about whether or not we have a mathematically complete theory. It's virtually impossible to develop a mathematically complete. In my opinion, this is virtually impossible to do that. You have to make some approximations, and then the question arises, are you bound by those approximations? So I was very sure that we really have to invoke quantum electrodynamics for a wide range from, I would actually say we have to invoke quantum electrodynamics for all processes in nature. So this is really concerned with the first group of topics. I haven't time to deal with all the other investigations which we carried out. And we came to 1983, and we asked ourselves the question, what about energy? If we add a certain amount of energy to a system, and we have a system in an extended quantum state, then will we be able to affect a nuclear process? Now that was simply a question, either you do or you do not. If you do, then it proves the point. If you do not, well, then you go home. And that had been lurking in the background. I seem to have lost the slide. I had actually wondered about this. Here is the gee whiz again. Let's go to the lab and charge some palladium cathodes with deuterium and see what happens. And I had found this very interesting set of papers by Alfred Köhn in 1947. And it made me realize that there was a possible way of inducing nuclear reactions under much more mild conditions. However, I did nothing about it until 1983, because quantum mechanics, of course, which was all I knew at that time, although 1947 was the critical year when Feynman, Tomonaga, and Schwinger, I think they got the Nobel Prize in 1947 for their work on quantum electrodynamics. But I was only an ignorant chemist. So by 1960, we had the unsatisfactory description of ions dissolution. By 1970, I had realized that deuterium in palladium was in an extended quantum system. And that made it possible, that raised the question whether we could do this experiment. Now I'll just show you this ancient idea. There are people here who are interested in surface-enhanced Raman spectroscopy, except I've lost the slide, so I won't show it to you. Let me deal with experiments of Alfred Köhn. In 1929, Alfred Köhn showed that you could take a palladium wire, you could charge it with hydrogen, because deuterium had not been discovered at that point, but you could charge it with hydrogen at this point, apply a field along the wire, and you could see that the hydrogen moved more rapidly to the negative end and less rapidly to the positive end. And here's an example of Alfred Köhn's measurements. You see here is the number of kinks accessed, and you can see that the negative one is accelerated, the positive one is retarded. If you reverse the polarity at the vertical dotted line, you can reverse the motion of the ions. Now, Giuliano Preparata and Emilio Giudice realized that I used to say that this experiment opened the way to some of the ultimate experiments of physics. And you will hear from Antonella Benino and Emilio Giudice about how this topic has been tackled in Frascati. My own attitude at the time was that I thought that you could make the, I'll just show you, this is an experiment which has never been done, but I still think it's a very good, possible experiment. You could make the great, put the palladium, put the deuterons into a grid of palladium wires, apply a field across it and put the laser radiation in, and enhance, see whether you could enhance the cross-section for the nuclear processes. So those of you who are in hot fusion will realize this is a souped-up version of inertial confinement. But, however, I was in the university, and I said, we cannot do this research in the university. Impossible. And what it actually led to, of course, we got extremely confusing results, but what it led to was surface-enhanced Raman spectroscopy, which was a field which developed a life of its own, in which I was only moderately interested. Well, we decided way back that we should investigate the energy balances. And this is our infamous isoparabolic calorimeter. It consists of a dual vessel means of calibrating the system with a joule heater and a cathode, polarized cathode in there, polarization of the cathode. And we wanted to see whether we could see any evidence of nuclear processes in this system. Well, we thought for a long time that the system was very precise, but not necessarily accurate. You know, if you have a scientific instrument, it can be accurate and precise. This is what you would like to have. It can be accurate but imprecise. You don't want to have that situation. The worst situation is that it is inaccurate and imprecise. But it can be inaccurate but precise. In other words, you get a precise measurement, but it is not necessarily the thing you want to see. So a lot of our early work was concerned with the notion that it was inaccurate but precise. So we used the heat, measured the heat transfer, in this way, and this is an example I've taken from the work done in the energy laboratory in Sapporo, that we could see the exothermic absorption of hydrogen, deuterium in palladium, and then we could see the buildup of excess energy. Now, I would say that it is extremely difficult to do these experiments and not see evidence of cold fusion. You really have to try very hard not to see it. It really is always there. But one of the problems which has beset this field is that you cannot calibrate an apparatus which has a random source of excess energy. If you ask yourself, can I possibly calibrate a calorimeter which has a random source of energy in it? The answer is no, you can't. So you have to do an adequate set of measurements with blank experiments. And eventually, I think here's perhaps a more direct illustration. I put this on for Mel Miles's benefit because we have to do some more work on this. That if you rely on the precise calibration of the, but not necessarily accurate calibration of the calorimeter, you can see that the energies you calculate are randomly distributed. That is, it's a normal distribution. However, eventually, we decided that this was wrong, that our concerns were quite incorrect, that the calorimeter was not precise but not necessarily accurate. It was in fact accurate and precise. And people could not understand why I was so my colleagues couldn't understand why I was so concerned with this point, with the need to do these measurements with a precise and accurate calorimeter. So let me just explain to you that, of course, I was not concerned with this from the point of view of experiments which we've done. I was concerned that we should move on to use nanotechnology in this system to generate heat in a palladium microwire. And the important point about this, so you have this, you have to be able to measure the excess energy accurately, but at a very low level. So I wanted, this experiment has not been done. I still think it's one of the ways in which you could produce a viable system. The reason, of course, is that if you have a micro structure, then the joule dissipation of heat is reduced by orders of magnitude compared to a planar structure. So if you have an array of microstructures, you will get a much lower input of energy, and the excess energy will become much more visible. In fact, if you do the calculations on this, you come to the conclusion that you might very well be able to make a device which gives you the Q value directly. That's the energy of the nuclear process involved directly. You polarize the system with a low current, and the excess, you measure the excess energy, and you can relate the excess energy to the current, and you should be able to get the Q value directly. That experiment has never been done. However, I will show you the illustration of the experiments of Stan Spark at the Naval Ocean Systems Laboratory. That's not called it anymore, what's it called? SPAWAR. He has deposited in situ palladium in the presence of deuterium. He's charged the deuterium into the palladium in situ, and he has looked at the temperature distribution with an infrared camera. Unfortunately, I haven't got the correct slide. You'd have to get Stan Spark to talk to you with a video of his experiments. And you can see from the infrared images that the temperature increases. You can see the temperature increase. And if you, you can sort of see it from this transparency here, that you can measure the time course. You can see flashes of light, although you can't see them because there are 10 microns in the infrared, so you need an infrared camera to see this. You can see flashes of light from the electrode. And if you, I'm convinced that if you classify these flashes of light, you can see whether it is in fact 24.7 MeV per flash. It is fairly straight, very tedious, but fairly straightforward procedure to develop this experiment to give you the Q value of the processes. Right. I have a little more time.
Yes.
I will go back to 1990. I've said this before, but let me go back to 1990 and just make a few remarks about hot fusion. This is the first paper on hot fusion by Oliphant, Hartek, and Lord Rutherford in Nature. Notice that it is just over half a page long. I issue a challenge to the whole audience. Try and publish a paper in Nature which is just over half a page long. You would never succeed. And what was so interesting about that paper, of course, is it just disappeared. A lot of this disappeared because deuterium was not, deuterium was called diplotron in those days. So if you do a literature search of deuterium, you won't find the early papers. And the one paper which you will not find in particular are the early papers of Philip D., who was also at the Cavendish laboratory. Have I a ruler? No. Okay. A pencil. Philip D. did the same thing. This was a titanium deuteride cathode bombarded with deuterons. And what Philip D. found, that this is the tritium plus proton channel, was that he had a fairly large number of tracks coming out at 180 degrees. 1934, this was. Previous paper was 1934. Here's another example. Not so clear because there's a mixture of tracks, but there's one set of tracks which is 180 degrees. And what Philip D. said was that this had to be the fusion of two deuterons which had lost their energy in the target. And this was totally forgotten in the time. And I still, Douglas Morrison, the late Douglas Morrison, who we are now missing, was very cross with, I think he was one of Philip D.'s research students, was very cross with me for saying that Philip D. had said that. But I said, well, Philip D. said it. Nothing I can do about it. That's what Philip D. said. And Professor Takahashi is here, whom we salute, because he has found that if you reduce the energy of the bombarding deuteron particles, you get other channels coming in. And of course, the question which I have always had in my mind, Professor Takahashi, is the D plus, we were very strongly criticized. We said we haven't got a nuclear ash, where's the helium? And we hear quite a bit about helium at this conference. And helium is we had seen helium, incidentally. We had seen helium in December 1988. But it was so strange that I persuaded my colleagues that we couldn't possibly talk about this. The question I have always had in my mind is there a helium-4 channel in a self-gathering neutron tube? In 1994, I decided I wanted to investigate this, but I couldn't get a self-gathering neutron tube because they've all been withdrawn. So they say. I don't believe it, but they have been. You can't get them anymore. But let me just skim through very quickly what else you see. If you use this calorimetry, which we have done, you see that these are the calibration pulses. Eventually, you see a very strange phenomenon here, which is positive feedback. You see that the application of the heater calibration pulse leads to an increase in the excess heat. And the system is driven to the boiling point. So let me just show you the evidence for positive feedback. Again, I will use some Japanese work, because people don't believe what we have done, so it is always better to use other people's data. So if you I have lost the critically important diagram, but if you proceed with the experiment, you find a situation that when you apply the calibration pulse, you do not get a steady state. So the application of the calibration pulse creates somehow a situation where more heat is generated in the system, and when you switch the calibration pulse off, this does not return to the baseline. So the calibration pulse, the increase in temperature, leads to an increase in thermal output. And I've mentioned this before. This is, and I think this will also become more clear from Antonella Benino and Emilio Giudice's presentation. When you get this increase, this marked increase in the excess heat, you get random oscillations. And this can be, they can be random or they can be regular. So you, I think the next other slide, this other slide is more interesting. And you have to avoid these oscillations. You have to drive the system so that you get it to the boiling point. You get these random oscillations. So there is positive feedback in the system. It has not been properly investigated. And eventually, of course, the cell, you can get a situation where the cell boils dry. And there are several people in the audience here who have observed this phenomenon. The cell, when the cell is dry, it stays hot. We call this phenomenon heat after death. Mike McCool, we call it heat after life. Giuliano Preparata, who's done some of the most interesting work, called it the after effect. And Giuliano Preparata, it is very easy. I mean, you know, you just have, it's nothing more straightforward than to show that you have an energy source in the system. You switch everything off and the thing stays hot. So what can you say about it? How can a calorimeter stay hot if there's no energy put in? And here's one of Giuliano Mengele's experiments. He had it stay, this is the excess heat. The excess heat, when you have switched it off at the boiling point, he could keep the system at the boiling point. When you switch it off, it stays hot. And this, he just got impatient, he switched it off after 8 days. So there is a means of generating heat without any input. Only you have to condition the system, of course, to give you that result. Finally, what we did, our final throw, was to say, well, we want to maintain boiling conditions in the system. So we built a set of calorimeters, which were in fact twin calorimeters, a lower section in which we could condition the experiment to go to the boiling point, and when it boiled, there was an upper section, and we extracted the heat in what is in effect a distillation column. So it was a calorimetric cell distillation column. And these are some experiments which we did in 1994. This is the excess heat in the lower section. When you get to the boiling point, of course, you can't measure anything in the lower section. This instrument becomes insensitive. But if you measure what happens in the top section, you have to calibrate the top section. That's the red line. And you measure the data points for the actual heat produced in the system. And this, although it was a very energy inefficient system, it did generate excess heat for 50 days at about 100% excess efficiency at about 4 kilowatts per cubic centimeter. So this type of methodology will allow you to make a system I was quite convinced that we could develop the system into a demonstration of generation of heat at about between, say 2 kilowatts per cubic centimeter for a prolonged length of time. Why it died on us on day 50, I don't know. It could be an accumulation of helium in the lattice destroying the electrode. Now, I should point out that this is not, all this work is difficult. You have to have the correct material, and you have to have a very open mind in tackling the subject. However, my esteemed colleagues from Frascati will show you that there is, that one can impose a great deal of sense and methodology on this, which makes the problem much more straightforward. So I will hand you on to Dr. De Nino. Thank you.
We have seen a lot of hands. Dr. Hora or Professor? Max?
Thank you. The question is first of all about the second law of thermodynamics. You may recall Hermann Haken's theory of what is called the synergetics, where if you have not a thermodynamically closed system, abgeschlossene system, then you can have this deviation. Question, have you thought about this? But before you give an answer, I have on a marginal question. Why is it called quantum electrodynamics, where you have collisions and motion of ions interacting, while quantum electrodynamics spinor equations show how the photon field appears by quantization of the electromagnetic field. You need for other processes. I don't see how this works for the collisions and motion of ions in an electrolyte. This is the second question. Perhaps you may say it very quickly first.
The question whether you have a closed thermodynamic system or not is always always very tricky, you know. I wouldn't go to the wall, as we say in England, on saying that this is a violation of the second law, but to me it looks like a violation of the second law. You can get around this. I would say, if you go that particular route, you get into the area which is known as saving the paradigm. I don't believe that you can save I believe that the system does violate the second law of thermodynamics. I mean, you mean the membranes? Well, I think the ions in solution violate the second law of thermodynamics. This way they violate Maxwell's equation. So you cannot do this. You know, it's a model. We always interpret the world in terms of the model, but that model is not right. You have to say, well, it's a kinematic, in the end you can do a kinematic interpretation of the behavior of ions in solution. If you want to have the dynamics, you have a kinematic interpretation. But if you want to have a fully dynamic interpretation, of course that comes much sooner than you think, because there is this structure of about 100 angstroms in the system, and the question is, it is really the quantum electrodynamics which determines the structure. I agree that then the behavior you can interpret in terms of quantum mechanics. You don't necessarily have to use quantum electrodynamics. You don't use quantum electrodynamics to interpret the behavior of the ions. I agree with that, yes. You need now a second generation of experiments where you explore the linkage to quantum chaos.
Okay, one more question.
I think this phenomenon didn't relate to the second law of thermodynamics. There is the source of energy release. This is nuclear reaction. We must consider the electromagnetic bound state emitting actually in electricity with little water and in discharge with hydrogen gas. Thank you.
就是说这个问题不破坏热力学第二定律，我们必须除了考虑核反应能之外，还要考虑电磁能放 X 线，特别是用氢左电解跟这个用氢气互动方面。谢谢。稍稍，就是啊，这感觉吧，对，不是破坏你这个附件。
As I understand, it's a comment instead of a question.
Well, that comment is welcome.
Let me say, he said just there is no violation of second thermodynamic law, and he said we have to consider the nuclear energy.
Well, of course, I mean, when we come to the second part of my lecture, when we come to the, eventually we pose the question, can we perturb a system with a weak perturbation? And if we have this coherent system, will we get in the coherent system a nuclear process? Then, of course, we say, okay, the nuclear process has to be part of the thermodynamic description. We have to have a nuclear description. And that does, I don't know, you can say it violates the second law because there's too much energy produced. But if you put the nuclear part in, it doesn't violate the second law. No, of course not.
We see one more from General Atomic, Dr. Yuan.
Yeah, I have a comment about your statement concerning the infrared images from Dr. Spot. You mentioned that there were flashes that were seen, and you associated these flashes with high energy particles. Now, the infrared camera is not sensitive to high energy particles.
No, I didn't say that.
Well, could you clarify your statement?
You see heat.
But you mentioned flashes.
Flashes of light. I mean, if you have a release of energy at a given point, you will get an increase in temperature. And you can see this on Stan Schwach's video camera, on the camera cases. You can see
you showed pictures of the increase.
Yes, you can see the temperature. And my thesis is that it has not been done, but my thesis is that if you classify the temperature excursions, it's a typical, it's a Green's function type analysis. You will be able to see how much heat is released at that point. Now, it may be that it's one point, or it may be that there are several sites, but you have the means. There is a very straightforward experiment, as I see. It's technically difficult, but it is a straightforward experiment to classify the temperature excursions and to say, what's the Q value for these processes? I think if you do this, you'll find it's 34.7 MeV.
Well, that's where I'm having a problem. I don't understand how you come to that conclusion from those images. These high energy particles cannot be seen by an infrared camera.
No, it's not the high energy particles. I think, Emilio, could we discuss this later, maybe? We can return. The question is, what is the cooling process in the nuclear transitions? That is a great big bag more of...
we can discuss it after.
Yeah. I think that after Emilio and Antonella's presentation, I think it would be more meaningful to discuss your point at that stage.
Yeah, here, Professor John Mallove.
For a short question, the laser diffraction experiment is very fascinating, and I have ideas about it. I'm curious what laser wavelengths you would cover.
Well, I mean, the palladium hydride absorbs in the blue. It's very fortunate. I mean, you could use an argon and focus it down. You can get a very high energy and if you have palladium diffraction grating and saturate this production and get to the state which Antonella, Benino, and Emilio de Giudice will describe, you would be well set up to see the interaction with electromagnetic radiation. You know, what experiments can be set up? That's one of the experiments we could set up. But I desisted. I was very self-disciplined. I said, no way. University of Southampton with nuclear experiments. No way. You could do it now. You do it.
Oh, you watch.
I'll watch.
Oh, Professor Arata.
Did you test after this experiment inside unknown atmosphere?
No, we did not.
You reported. I immediately test in argon. So after this, nothing.
Well, it's very easy to get a system which does not show heat after this. But if you show, Giuliano Mengele's experiment, I think is very interesting. And what can you say about that? It's a sealed system. It's got the deuterium atmosphere in there, and it shows excess. It stays at the high temperature for 8 days. Well, I don't know what happens in an argon atmosphere. Maybe in an argon atmosphere.
I tested.
Well, fine. In an argon atmosphere, you see nothing. That's okay. You have to take that into account. Maybe it degasses in an argon atmosphere. I don't know. Could be. I don't think you'll necessarily do it that way, but we've also seen heat after death in the electrodiffusion system. It's just a way. It is one way in which you could get an increased energy efficiency. You use pulse. Here is the pulse electrolysis man next to you. You use pulse electrolysis, and you would get an increased energy efficiency.
Dr. Violante.
Just a moment, Martin. Talking about the ion flux through the pole, it is well described by the Saxon equation for the electrostreaming phenomenon that takes place when you apply a difference of pressure creating a difference of voltage, or when you apply a difference of voltage creating a difference of pressure. And this is well described by means of the Saxon equation that have been experimentally proved. So for a zero value of the production entropy function, the force terms of the flux equation should drop, and we shouldn't have any ion flux through the pole. This is my question.
Well, if you believe all the work which has been done, I once listened to De Boer, who was the research director of Philips, give a lecture on these properties, and the conclusion was that he didn't understand anything whatsoever. Although some people maintain that you understand this, I don't think you do. Let me just pose a question to you in return. If you have, which originates with Giuliano Pepperata, if you have a reverse osmosis membrane, it lets through water. You use this other system, which has smaller pores, and it only lets through ions. How can this possibly be? Well, one thing lets through the coherent fraction, another thing lets through the incoherent fraction. That's the straightforward interpretation. Now, I don't believe that all these, what are they called in video? These properties, streaming potentials and, no, what are they called, Vittorio?
What do you mean?
The general description, the general field of work.
I don't understand, sorry.
Well, all these groups of phenomena
are
covered by an all-embracing title, and I've forgotten the title.
You mean the electrostreaming phenomenon?
Yeah, the whole bunch of phenomena.
Yeah, it's transport phenomena regulated by not reversible thermodynamics across a membrane.
No, that's not the description I want. But anyway, I don't believe any of that. I'm sorry, I don't believe.
You don't believe?
I don't believe any of that.
Saxon equation have been proved.
Well, I'm sorry, but I don't believe any of the work which has been done on those type of systems. I mean, you have interpretations based on high frequency measurements on conductivity of RNC solution. I don't believe any of that either. Well, I think that if you do it again, you'll find it's quite different.
We use this equation for dimensioning our membrane system.
Well, good luck to you.
Any more questions? If not, let's thank Professor Martin Fleischmann again. I believe Dr. Nino is ready to provide more supplement.
Excuse me.
Any volunteers to help us move this desk this way? Any volunteers? We move this desk to this. Let's give them much space. Yeah, move together. More volunteers. It doesn't work. It's not. Just wait. Okay, thank you everyone.
Not very well, guys.
就是他这个这样做是有够的，对，拿另外一张图。
那个机理，把那个灯熄掉。前面这个。过来。行。
This work has been done in a collaboration between NEA and IMFF, two main governmental institutions, scientific institutions in Italy. This is a summary presentation. What we have done was to design an experiment in order to prove a straight line of thoughts that we started this project 2 years ago under the guide of Giuliano Preparata, and we concluded we hope we are almost to conclude the work in these weeks. We have designed an experiment with the aim of studying the loading of hydrogen and palladium in thin films, because we want to prove the influence of the longitudinal electrical potential on the cathode in order to test what was called in the past year the Kenarov effect, and now we renamed it Preparata effect. To do this, we need to have very peculiar structure, very long and tiny thin films, in order to have a voltage drop across the cathode. This was aimed to obtain very reproducible experiment of excess heat and check in real time helium for production. We set up an experiment in which it's possible to measure helium each half an hour, 40 minutes. It depends on the dynamics of the experiment, but it is important that we are able to check if there is helium production during the experiment, and not to have only the integral amount of helium produced at the end of the experiment. This way, we can have a parallel calorimetry more reliable, because we will be able, at the end of this work, to collect all the helium atoms produced in the cell. So this is another calorimetry parallel to the usual thermal calorimetry we used in the past. These are the geometry we choose to prove this effect. This is a palladium cathode. It's a thin film deposition on different substrates, and the dimensions are written down there. As you can see, it's a very tiny structure, 2 microns thick, 54 microns wide, and 100 centimeters long. This assures us a big voltage drop across it during the electrolysis, only induced by the electrolysis current. As you can see, the dimension of the cathode are very small, very tiny dimension, very small amount of quantity of materials. Then the heat production we expected is of course very small in absolute values. To obtain cathode in this such a way, it's not easy, as many among you know. To obtain reproducible experiment, we need, it's very important to have very reproducible cathode that doesn't peel off during the experiment and survive to a loading of hydrogen loading. You know that when hydrogen enters into palladium lattice, it deforms the lattice up to 10% of its dimension. So it's very difficult to convince the palladium film to stay on the substrate during the loading and eventually during the heat production. So we worked very hard on the production of thin films, and we found that we have to check every part of the process of production in order to obtain good results. It's very important, the selection of the substrate. We tested several substrates such as alumina, silicon crystal, sapphire, and the best result we obtained in terms of mechanical properties were obtained on alumina substrates. But even the sputtering procedure is very important in terms of the argon pressure in the vacuum chamber, and in terms of duration is the definition of the mask and the etching of the structure that must be done through ion etching and not through chemical etching, because we found that there is a severe under etching when you use acid. But in any case, many more details will be available in the poster session this afternoon. In the poster session, I will show you the characterization of this sample. The results, now here I'm interested in showing to you the results. The result is a very good adhesion in substrate and the possibility to have several load and deload cycles. We test up to 4 or 5 different cycles on the same sample, and obtain each time high loading ratio using the technique of preparata effect. And we obtain XSC too as soon we overcome the threshold. And excess power here ranges from 3 to 4 kilowatt per cubic centimeter. This is an example of 2 different cycles, load and deload cycles on the same sample. As you can see, I can show you. This is the first maximum here, with the current on, a decrease in the resistance that corresponds to an increase in concentration. And this is the other one is the deloading maximum peak. As you can see, this is the other cycle. It's almost similar. This is almost the same qualitatively. This is the first maximum. This is the loading. As you can see, we went down under 1 of error naught. And this is the deloading. This is just to show you as is it possible to obtain cathodes that are able to cycle several times and every time obtain very high loading and excess heat. In this picture here, we can compare the electrical parameter to the resistance curves. You see here that the cathode, the voltage drop across the cathode induced by electrolytical current into the cell is high, up to 35 volts. After the maximum, at a certain point, when you increase the voltage, there is a dramatic drop of the resistance that corresponds to a dramatic increase in the loading of palladium. This loading status goes away until you remove the potential. At this point, you deload the systems. In this experiment here, we obtained the increase in the concentration when we increase the potential. This is another experiment in which we fixed the electrical parameters just at the beginning of the experiment, and the system exhibits a drop, spontaneous drop, at a certain point of its loading. That corresponds to the end of the beta phase. This is a spontaneous drop, as you can see. The scale is different from the previous graph I showed you, but qualitatively it's almost the same. There are very small adjustments that could be done on this picture here, but those among you that are interested in these topics can discuss it in the poster session. And as soon after the drop in the resistance, the increase in the loading, you can see the comparison of a delta power in a time that is the constant time of the calorimeter. In this case, you can see this is about 500, 600 seconds. The time constant of our calorimeter, the tau of our calorimeter, is 160 seconds. So, and this effect is fully reproducible. We obtained several times this kind of samples. We tested different samples on different substrates in order to improve the calorimetry. Calorimetry is obtained putting in a very good thermal contact the substrate of the deposition with the Peltier element, the commercial Peltier element. This way we measure the voltage across the Peltier element and avoid to lose heat in heating the water of the cell, and avoid to lose heat through film boiling effect. It's a quite good calorimetry, but it's not enough, as you will see in a moment. So what Professor Flashman said before is that calorimetry of a coherent nuclear process is not a trivial thing. It's not unusual calorimetry. Let's try to understand what we mean for a coherent nuclear process. Here, I don't want to give a demonstration of what I'm saying because it's out of the scope of this presentation, but you can find all the details in Giuliano Preparata's book. We can discuss it later if you want, but we know that when a high fraction of PDD electrons is in the coherent state, it is possible to have the formation of a very hot deep nucleus. It has a certain time to break down, and this time is less than 5 per 10 to minus 22 seconds. In this time, in a time shorter than this particular time, you have a very, very hot DD nucleus that has 24 MeV of energy. It can eventually lose its energy in only one strike, giving 24 MeV to the lattice. Now, 24 MeV corresponds to a wavelength of 10 Fermi. That is enough to heat a single palladium nucleus and eventually generate transmutation. More than transmutation, we can call it photofission, a certain kind of photofission that is due to the coupling of the nucleus, palladium nucleus, to a very energetic field, a field that has 24 MeV. So it is shaped by this field. after this time, if nothing happened with this time, it is a small probability to happen after this time. There is a coupling, a very strong coupling between this energy, this gamma ray field, and the field of coherent field present in the matter, the field generated by the deuterons in the coherent state. At this point, the energy is thermalized in the lattice. The thermalization can happen through the emission of soft X-rays. The X-rays are due to the presence of d electrons, coherent, almost free electrons present in the lattice. They can receive this energy, and they can eventually release it in the form of X-rays, and the maximum frequency is 100, maximum energy is 100 eV. It is the maximum plasma frequency of this particular class of electrons. And then starts the cooling of the process. This is a very hot process. A nuclear process is a very hot process. So what we learned by thermodynamics is that radiation loss is proportional to T to the 4. If this is, and it is a very hot process, the main channel of the thermalization is via electromagnetic radiation. So it is a big error to believe that calorimetry can be done just thermalizing, measuring energy that thermalizes near the cathode. Near the cathode thermalizes just a small percentage of the energy, but most of the energy goes away in form of infrared radiation, as the Stefan Boltzmann laws teach us. Another important part of energy can be loosened in boiling, film boiling effect. I mean that if the cathode increases its temperature, a small gouge of very hot gas forms at the surface. This has the effect to mismatch thermally, to produce a thermal mismatch between the cathode and the solution. So if you try to measure heat, putting a thermometer inside the water of the cell, you lose an important amount of this heat. That is only a part of the total heat produced in a nuclear reaction. So it's not so easy to set up a good calorimetry. And Martin Fleischmann